Okay, so in this problem, we want to find the maximum positive moment that can be developed at point C right here. And it's going to be due to a single concentrated live load. That's a load that moves around. A uniform live load. And a dead load. So I'll also show you how to handle uniform loads that are live and dead. So the first step is going to be to draw the influence line for the moment at C. So in our previous strategy, we always go to that point and we cut the structure and we decide we'll work the left side or the right side. I think we'll work the left side. And to do that, I'm going to need to find the reaction at A. I think we just worked this problem, didn't we?
It was the same, but 5 feet instead of 4 feet.
Oh, well, we got to do it again. That's too bad. Okay, so let's come over here. And our unit load will be there. We'll have our reaction at A and our reaction at B. This distance is 8 feet and this is 4 feet. Remember, this is X. So if we sum the moments at B and put an equilibrium, we should be able to solve for AY as a function of the moving unit load. So we'll do that. So about B, the unit load creates positive moment. And this distance here is 8 minus X. Then the reaction at A creates negative bending moment with a moment arm of 8. So AY is going to be 1 minus X over 8. So I'll come back over here and look at my left side free body that is 4 feet long. And I'm only concerned about the moment right now, so I'll draw the positive moment at C. My reaction at A, well, we just found that. It's 1 minus X over 8. And we'll be concerned first with the unit load being there at a distance X. So we're going to solve for the moment at C. We can do that by summing moments at C, making sure the whole free body is in equilibrium. So first, on the right-hand side, that moment is positive. The moment about C caused by the unit load is also positive. And then what's this distance right here? It would be 4 minus X. And then I'll have my reaction at AY. That's creating negative moment. So the force is 1 minus X over 8. And what's the moment arm, this distance? 4. Did I leave anything out? So let's solve for the moment at C. So that 4 cancels, that 4 cancels. We got X. Oh, it's a half again, isn't it? And then we'll do it again. Oh, I forgot to label this. This is going to be when X is between 0 and 4, and this one's going to be between 4 and 12. Sorry about that. Let's squeeze those in. Doesn't look very nice, but there it is. So again, my reaction is still the same. 1 minus X over 8. There's my moment. Except our unit load has bent Hilbert to the right side. So we'll sum moments again. So we're summing at C, making sure we're in equilibrium. So again, the internal moment MC is positive, and I have just this reaction that creates a negative moment. The load is 1 minus X over 8. the distance is 4. So if you solve for the moment at C, looks like you're going to get 4 minus x over 2. Okay? So now we can plot the moment at C as we run this way. So from 0 to 4, it's x over 2. So when x is 0, we get 0. When x is 4, we get 2. And then from 4 to 12, I have to use this equation. At x equal 4, I get 2. At x equal 8, I get 0. At x equal 12, I get minus 2. So there's my influence line for the moment at C. Now the question wants the positive moment. So where do I put my single live load of 8 kips on this structure according to my graph to create the largest positive moment? I put it right there, which is at x equal 4. So if I keep track of this, my live load, concentrated force, what do I get? I get 8 kips times 2, which is 16 kips. Oh, I'm sorry. This has units of feet. So it'll be 16 kip feet. This is 2 feet. Okay? Now let's talk about the difference between a live dead load and a uniform load and a dead load. Okay, dead load, you don't get any control. Dead load goes all the way across the whole structure. It's like self-weight, right? So we'll do the dead version first. So what we have to do is take the dead load, which is 1 kip per foot, just like we talked about, and I have to multiply it by the area under the whole curve. Okay? Now, all these shapes are triangles, so they're going to be 1/2 the base times the height. So the first triangle has a base of 8 feet and a height of 2 feet. This little triangle here has a base of 4 feet and a height of minus 2 feet. So what's that equal to? Looks like 4. You guys get 4? Yes? No?
Yeah. 4.
Yes. 16 minus 8 is 8. Take half is 4 times 1 is 4. So this will end up being positive 4 kip feet. Now this is the part that you're not going to like. I just sense it. Oh, it's live uniform load. Now in a live uniform load, kind of as the engineer, you have to determine where should I start and stop a uniform load to create the maximum positive effect. Why positive? Because that's what I'm looking for. Should I include any of this area? No, because it's generating negative effect. So this load is only going to start at 0 and go to 8. So that has a load of 3 kips per foot. And again, I'm going to get the area under this part of the curve, which again is a triangle, so it's 1/2, and the base is 8, and the height is 2. That gives me 24 kip feet. So when I write the moment at C, what's the maximum value? I have to add all this up. So I got 16 plus 4 is 20, plus 24 is 44. So what would that look like if I actually drew on top of the structure what the load looked like? Well, for one thing, the dead load would go over the whole structure. Right? Where would the live uniform load go? Just from here to there. And then where would the concentrated load go? So this is now the loading scenario. Dead load over the whole structure, live over the first 8 feet, concentrated load at x equal 4, and that would create the maximum moment at C. What if I wanted the maximum negative moment? Well, this would go out to the end to create a negative value. What happens with my dead load? It just is. It's going to be exactly the same. Where does my live uniform load go? Just over the last 4 feet. Mr. Van Tilburg.
How do we know that our live uniform load would be 8 feet?
Because I'm starting it and stopping it so it just covers the positive parts of the influence line.
Why is that?
Because I want the largest positive value. So I'm going to start. I'm going to start my 3 kip force here and go to there. If I cut it shorter, it would be smaller. If I go farther, I would get a smaller value too because I'd be including negative areas. So I'm only going to include the positive areas for positive and just the negative areas for negative.
Okay.
For the live one. Now for the dead one, full structure.
Right.
And of course, we already talked about this all day. This can be anywhere it wants to be to create the value.
So depending on where that is, that changes where your live load will be, where your distributed live load.
No, they're independent of all that. These are only positioned based on this graph. They don't care where the other one is. My uniform live load does not change if this moves to some other flip position. That's the place where it creates the largest positive effect. If I made it any smaller, right, then the effect would be smaller.
Yeah.
If I went too far over here and got negative, the effect would be smaller. So that's the maximum positive effect. Okay.
That arrow right there, in the center of the live load, that's the concentrated live load.
This one here? Yeah. Right now we don't have anything else for concentrated loads except live.
And then, how did you